to everyone present here. Today we are going to start the session 3 of Unit 2, that is combinational mass logic circuits. Already we have discussed about the static CMOS. So we are seeing the design consideration. While we want to design any circuits, we have to consider these all the points. So last class we have seen what is input delay ordering effect. That means the gate will work faster when an inner input arrives later than the outer input. So here the input A is nothing but inner input and B is the outer input, because outer input is connected very close to the power rail such as VDD or grounded. Whereas the inner input means which is very close to our output. So this input is arrived later than the outer input. Our gate will work faster, right? That we have already seen. The next design consideration is asymmetric gates. Actually, if any one of the input is far less critical than the other, we can convert our symmetrical gate into asymmetrical gate to favor that particular input. Okay. For example, I am taking this circuit. In this circuit, we have two inputs. One input is A and another input is B. Okay. So in this, which one is critical means definitely the input A is the critical one. Okay. Because the A will be keep on changing, but the reset will be used once in a while. So the reset button is always less critical than the input A. So here, in order to favor the input A, we can convert the symmetrical gate into asymmetrical gate. Symmetrical gate means you know that this is our NAND gate, right? Already we know how to design this. This is our NAND gate. And here it is NMOS, that is pull down network consists of NMOS and pull up network consists of PMOS, right? So this is our design. So in this design, all the width of the transistors are 2, right? So because of this width, what happened? It will produce the resistance of R by 2, because R by K for each NMOS, the width is 2, no? So R by 2. Plus here also R by 2, the total resistance is R. Here we have chosen the width is 2 for PMOS. So individually we have to calculate the resistance. So here for PMOS, the formula is 2R by K. Here K is nothing but the 2. Thereby individually the transistor contributing the resistance of R. So falling also R, rising also R. So equal rise and fall delay, that's why it is called symmetric. Equal rise and fall delay. That's why this type of gate is called as symmetrical gate. So we have to convert the symmetrical gate into asymmetrical gate. See here, I will choose the width of the transistor in such a way that I have to favor my input A. How to favor is, see here I have to choose the width of the transistor, this transistor in such a way that it must produce the resistance of R. Anyway, it has to produce the resistance of R. How to choose the resistance R means, see here if I am choosing the width is 4 by 3. 4 by 3 means this transistor contributing the resistance of R by K. No. So R by K is nothing but 4 by 3. So thereby 3R by 4 is the resistance contributed by this transistor. And for this transistor, the resistance is nothing but the R by 4. Anyway, both we have to add together. So 3R by 4 plus R by 4, I am getting 4R by 4, which is nothing but R. See, anyway, these two transistors connectively producing the resistance of R, but the width will be chosen differently. For this transistor, the width is 4. This transistor width is 4 by 3. So it is called asymmetric gate. The width of the transistor will be different, right? Both the NMOS is not having a same width. So this is called asymmetric gate. So what is the speciality of this asymmetric gate is, see here, whenever if you want to calculate the logical effort at A, input A for the symmetrical gate. So this input A is connected to one PMOS and one NMOS. So NMOS and PMOS both are having the width of 2, here also 2. Thereby total capacitance at the input A is 4C capacitance. So logical effort formula is input capacitance of this gate divided by input capacitance of the inverter. Inverter always we have the capacitance is 3C. So it is 4 by 3 is the logical effort of this one. Okay. Whereas we are going to calculate the logical effort for the asymmetrical gate of this. So here GA equal to, so at the input A it is connected to this PMOS transistor with this one, thereby here I am having one capacitance, right? And similarly here also we have another this is connected to this this input A is connected to here, that is 4 by 3, this is 1 by 1C, right? So here how much capacitance is? It is nothing but the 4 by 3 capacitance. So totally 4 by 3 plus 1C capacitance. So how much it is divided by, we know that inverter having 3C. So here 10C by 3. So which is nothing but the 3 point, sorry, here it is 10C by 9C. So 9C means it is 1 point something, right? So here it is 1.133, but here the logical effort is 1.11. So logical effort is lesser for this asymmetrical gate when compared to symmetrical gate. Okay. So if the logical effort is lesser means, as we all know that it is, the delay will be lesser, because the delay is nothing but the parasitic delay plus product of logical effort as well as electrical effort. If G is lesser, the delay will be lesser. If delay is lesser, the speed will be higher. That's why we have to convert, if any one of the input is far less critical than the other, we can convert the symmetrical gate into asymmetrical gate by choosing the different width, right? So as I hope that everyone clear about this. The next consideration is skewed gates. What is meant by skewed gate is, suppose when one input transition is more important than the other. We have two transition, one is falling, another one is rising, right? So falling transition is, if you want to favor the rising transition, rising output, we have to go for the I skewed gates. Okay, if you want to favor the falling transition, we have to go for the low skewed gates. Unskewed gate means it won't favor any of the transition, both the transition are equal. Okay, that is called unskewed gates. Okay, both the transition are equal. See here, the logical effort of rising as well as falling. Rising means GU represented by GU, falling is represented by GD. Both are equally 1, so it is unskewed. Here also another example for the two input NAND gate. Both rising as well as falling logical effort is same. Okay, that's why it is called unskewed. There is no favorism for any of the transition. But if you want to favor the rising transition, we have to go for the I skewed inverter. If you want to favor the falling transition, we go for the low skewed gates. Okay, first we will start with the inverter, then we are going to see the two input NAND gate. For the I skewed inverter, see here how to convert the this how to design the I skewed gates and low skewed gate means, see here the favorism can be done by decreasing the size of the non-critical transistor. See here for the high skewed, it is favor the rising transition, right? The high skewed is favoring the rising, whereas low skewed is favoring the falling transition. Okay, So rising is who is responsible out of P mass and N masses. Definitely the rising is responsible by P mass, because if it is 1, you will be getting output is 1. So P mass is whole proprietor, or is the person who is giving the or responsible for the rising transition, right? So here, if you want to calculate the logical effort for rising transition, you have to compare this high skewed inverter with the unskewed inverter. It should having both are with this 2. That is, both has to produce a resistance R. So if you are comparing these two, I already told you logical effort is a formula which is equivalent to input capacitance of the high skewed inverter. Input capacitance, how much it is? Here it is 2, it is half. So totally 2 plus 1 by 2 capacitance at the input side. Whereas in the unskewed inverter, the capacitance is 3C. So the logical effort for the rising is 2 plus 1 by 2C is nothing but the 5 by 2C divided by, here I am having 3C. So how much it is? 5 by 2C divided by 3C, it will become 5 by 6. Similarly, falling transition, how we have to calculate the falling transition, GD now. See here, for calculating GD, here the width is half, so we should not consider this unskewed inverter. Instead of that, this is also unskewed inverter. Unskewed means both are having equal resistance. Okay, see here, width is 2 means resistance is 2 R by K, so it is R. Similarly, here the width is 1 means the resistance is R. So both are equal resistance, so it is unskewed. Similarly, here also the width is 1, but it is 2 R by 1. Here R by 1 by 2 is nothing but again it produces 2 R resistance. Anyway, both are producing same 2 R resistance, so it is also called unskewed inverter, right? So to calculating the falling transition GD for the high skewed inverter, we have to compare with the unskewed inverter, this one. So because the width is here, it is half, here also half. So here the width, the capacitance at the input side is here also 5 by 2 into C divided by, here it is the capacitance at the input side is 1 plus 1 by 2 into C, which is nothing but the 3 by 2 into C. So if I am dividing 5 by 2 into C divided by 3 by 2 into C, I will get what? 5 by 3, right? So average is nothing but the 5 by 6 plus 5 by 3. Average is 5 by 6 plus 5 by 3 divided by 2. You will be getting 5 by 4, right? Similarly, low skewed inverter, you have to calculate the logical effort for rising transition and falling transition. For rising transition, we have to consider this inverter, because the width here is 1, here also 1, right? So what is the input capacitance here is, it is 2C capacitance, because it contributing 1 capacitance, is contributing 1 capacitance, totally 2 capacitance at the input side of A. Similarly, for this consideration of unskewed inverter, the input capacitance 3 by 2C. So GU for this is nothing but the 2C divided by 3 by 2 into C. So you will be getting 4 by 3, right? Similarly, if you want to calculate the falling transition, you should not consider this inverter. Instead of that, we have to consider this one, because here also with this one, here also with this one. Okay, so here with capacitance is 2C, here 3C. That's why we are having 2C by 3C. You will be getting 2 by 3, right? So the average is nothing but the what? 4 by 3, 4 by 3 plus 2 by 3 divided by 2. So you will be getting 1. So like that, we have to calculate the logical effort for the high skewed as well as low skewed inverters. Okay. Similarly, for the NAND gate, I will explain you how to design, how to calculate the logical effort. So this is the unskewed NAND gate, right? So rising as well as falling, both are having the equal 4 by 3. So it's called unskewed. The average is 4 by 3 plus 4 by 3 divided by 2, you'll be getting 4 by 3 only, the average. So if you want to calculate the high skewed NAND gate for high, that is a rising transition GU, we have to consider the rising, that is y equal to 1. So if A or B, any one is on, you will be getting output equal to 1. So we can consider any one input A or B. Okay. Suppose if I'm considering the input A, this is connected to both PMOS and NMOS. So totally 3 capacitance will be available at this point because it is contributing to capacitance and this contributing 1 capacitance, totally 3 capacitance. So you know the formula, 3 capacitance divided by the same, we have to use the inverter. Okay, always we have to compare with the inverter. Inverter is a reference. So you are comparing with the this inverter because it is having the resistance of R. It will also produces the contributing resistance of R. So I have to consider this inverter. Input capacitance is 3C. So 3C by 3C will be getting 1. Similarly, if you want to calculate the falling transition, you have to consider, that is compare with the this inverter because it will provide the resistance of 2R. It is also providing R plus R. It will provide 2R, right? So we have to compare this with this inverter, right? So falling transition, see here, we can consider any one input. So the same way I'm considering the input A, I'm having 3C capacitance. Okay, divided by, now here it is 3 by 2 capacitance. So you will be getting what? 3 will be cancelled 2. So this is falling transition. So average is nothing but the here 1 plus 2, right? 1 plus 2 divided by 2. You will be getting 3 by 2. So this is our average logical effort. So like this we have to calculate the logical effort for any gates. Okay, so we have to remember two unskewed inverter, this one as well as this one. Okay, these two unskewed inverter we have to use for all the gates, right? The next last design consideration is this P by N ratio. See, the best P by N ratio of any logic gate is the ratio of PMOS to NMOS transistor width. Okay, see here, if you want to make the if you want to make the gate faster, I have to use the formula, that is the width of PMOS I have to choose must be equivalent to root of the PMOS width divided by NMOS width. Right? Generally, for the unskewed inverter, we have the width is PMOS is 2, NMOS is 1. Thereby, the width of PMOS, we have to choose root 2. Root 2 is nothing but the 1.414. So, if we are choosing like this, PMOS width is 1.414, the delay will be reduced. Okay. So, with this, I am going to conclude the session. Next, we are going to start the pseudo NMOS, the next circuit. Thank you all.